most important thing about the Laplace transform, at least for us. So notice that under the proper hypotheses, one can iterate. One can iterate this, right? So the Laplace transform of the second derivative, well, that's going to be S of the Laplace transform of the first derivative. Okay, that's S of the Laplace transform of the first derivative minus the derivative at 0. Right? But the Laplace transform of the first derivative, you remember, is the Laplace transform is, S times the Laplace transform of the function minus the function evaluated at 0. Right? And so you get the Laplace transform of the second derivative is going to be S squared times the Laplace transform of the function minus S times the function evaluated at 0 minus F times 0. Yeah.
Is this going to turn back into power series?
No, don't worry.
Okay.
Not.
I mean, but could it though? In theory, like if you're dealing with like something like fractals or something like that.
So
that goes on infinitely.
So you're saying, suppose you have, if you take the Laplace transform of a power series,
yeah,
then you would get some sort of, yeah, it would.
Okay.
It would. But that's not what we're going to use.
Right. Yeah. No, I was just wondering.
Yeah. It would. We'll do it in a much simpler way. We'll use it in a much simpler way. Okay, so is everyone okay with that? Second derivative, you see how the second derivative, you iterate blah, blah, blah. And if you were talking about the nth derivative, right, you end up with if you have the nth derivative, then you end up with S to the n times the Laplace transform of f minus S to the n minus 1, f at 0 minus blah, 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 down to S. The second derivative at 0 minus the first derivative.
So in the middle of the blah blah blah, you have like S to the n minus 2 f prime.
F prime.
Right. So it's like there's.
That's right. They're moving in opposite directions. Yeah. Maybe I should break down the. Yeah.
When you say iterate this for the second, are you just talking about how we can find that one enters the ones before?
Yes, exactly. So maybe I should write down the conditions. So as I said, like under the proper conditions. So what one needs the conditions are that you need f prime, double prime, f to the n minus 1th derivative to be continuous, and you also need each of them to satisfy the exponential type condition, as you expect. they all have to satisfy the same condition. And you need the nth derivative to be continuous, piecewise continuous. So if these three conditions are satisfied, then we love given this term. Then you can take the Laplace transform of the nth derivative.
Is that supposed to be f prime is 0 for the Sn minus 1 term? On the thing you just boxed,
Yes.
should that be f prime is 0 on the s to the n minus 1 term?
No.
No?
Nope.
Okay.
It's just like here. Like you ended up with an F.
Okay.
So let me see if I can show you how this works out. So let me see if I can do it. So how do we use this to solve initial line problems? So here's going to be I'll just show you an example. Suppose we have a differential equation that looks like this, and this is one that we can probably solve without doing this, but we're going to do it by using the Laplace transform. Okay. So you have this differential equation. Let's, instead of solving it by a similar method, we're just going to hit everything with the Laplace transform. We hit everything with the Laplace transform. The Laplace transform, notice that Laplace transform is linear. Right? It's a linear transformation because it's a linear operator because it's an integration. Right? And so we can pull out, we can separate this. We can pull out the constants and such. So L of y prime is equal to L of y over y. And we're going to try and figure out something about L of y prime. Okay. I'm sorry, L of y. Right? We want to figure out something about L of y, because y is our solution. So, well, from what we just saw, L of y prime, this thing is s times L of y minus y at time 0. And we also saw that L of e to the at was 1 over s minus a. Right? So we can use that for this guy, and we get minus 4, 1 over s plus 1. Y naught was 1 from the initial value condition. And so if you solve for L of y, well, you end up with you get 1 over s minus 1 minus 4 over s minus 1 s plus 1. So that's just algebra. Just solve for Ly. Just solve for Ly, and that's what you get. Okay, so you see what happens. When you start off with your differential equation, you hit everything with a Laplace transform. You say, okay, well, I'm looking for the y that makes this work. The y that makes this work would have to have the property that L of y is this. Okay, L of y is this rational function. Okay. So at this point, if you had an inverse Laplace transform, you would use it. You would say, I now use the inverse Laplace transform, and I know that y has got to be the inverse Laplace transform of this thing, the end. Okay, and this is basically what we'll do, although not so plainly. Okay. Yeah, here.
Will the inverse Laplace transform end up getting rid of those s's? Because like at this moment, like we don't have a solution for the s's, do we?
So these s's are just variables, right?
Yeah.
Right. I mean, in some sense, the inverse Laplace transform is turning these guys back to the functions of t. Yeah, if that's what you're asking.
Yeah.
Yes.
Okay.
Okay. Okay. So we don't have the inverse Laplace transform at hand, but we can still solve this sort of thing using elementary tricks. Okay. So what we'll do is we'll say, well, look. So notice, and you're not going to like this. F over 4 s minus 1 or s plus 1 can be expressed as a over s minus 1 plus b over s plus 1 by partial fraction decomposition. By partial fraction decomposition. Is everyone okay with partial fraction decomposition?
Why can't we just say, why can't we just make the inverse go to each one and then just say that's like e to the negative t and then 4 sine or cosine, whatever?
Well, that's basically what we're going to do. That's basically what we're going to do. But we'll simplify this thing first before doing that. Okay, so yeah, so what we'll do is say, well, this thing here is actually 2 over s minus 1 minus 2 over s plus 1. Okay, so in that case, y is going to be the inverse Laplace transform of 1 over s minus 1 minus 2 over s minus 1 minus plus 2 over s plus 1. Okay. And so what you end up with, the inverse Laplace transform is also linear. And so what you end up with is negative L inverse of 1 over s minus 1 plus 2 L inverse of 1 over s plus 1. Right, because we've got a negative 1. We've got a negative 1 here. Right? So the negative 1 L inverse of 1 over s minus 1. 2 of L inverse of 1 over s plus 1. Right? And then we use the calculation that we did earlier. Right? L of e to the at is 1 over s minus a. Right? And so for that one, we already know, right, that L inverse of 1 over s minus a is e to the at. Even though we don't know the Laplace transform's inverse, we do know this, right? And so we end up with negative e to the t plus 2e to the negative. So this is how the Laplace transform changes a differential equation into basically a partial fraction decomposition problem. And then we'll do that. Any questions? Okay, that's it. Oh, I have examples to return to. Quinn. Johnson, Christie. Johnny. Mary. Shannon. Georgia. Carla. Where is Carla?
She's, feeling terrible.
Okay.
I have to pick it up for her, but
Christina. Elsa. Brian Yamamoto. And Brian Zuckerman.